Hello, everyone, and welcome to another UK Quantum Fluids Network webinar. Today's speaker is Srivatsa Babari Prasad from Newcastle University, and he's going to talk about vortex dynamics in dipolar superfluids.
Okay, the audio is great. Okay, perfect. Thank you for the invitation to speak today. It's a real pleasure to be speaking to you today. I'm going to be talking today about vortex dynamics in superfluids with long-ranged and anisotropic interactions, such as in BECs with dipole-dipole interactions. And I'll be talking about some subtleties in the nature of single vortices and vortex dynamics that for some reason, haven't really been explored yet. Most of you will be familiar with classical vortices. These have been studied for more than 500 years from the time of Da Vinci, and they pop up across a wide range of scales from the subatomic all the way to cosmological scales. So we have some classical examples here, such as a cyclone or a hurricane, and also a galaxy. And this is characterized by this quantity vorticity, the curl of the velocity field of the fluid, which is going to be non-zero. And in the quantum realm, we have vorticity again, which pops up in several different contexts. For instance, in a superconductor with Abrikosov vortices, and also in a Bose-Einstein condensate with quantum vortex lattices over here in this experiment. And the difference between classical and quantum vortices is that whereas the vorticity of classical vortices can take on any value, due to topological constraints, we instead have quantum vorticity taking on only integer values of this quantum h bar over m. And similarly, the circulation of a vortex around the core of the vortex is quantized as such. To specialize to two dimensions, quantum vortices are irrotational outside the vortex core, have a quantized vorticity, as I mentioned. And one thing to note is that for vorticities higher than n equals 1, although they can in principle exist, these will be unstable to breaking up into smaller vortices if you have a quantum of larger than 1. So one approximation that's often made with quantum vortices is that if you assume incompressibility of the fluid and that the distances between vortices are sufficiently large, the dynamics of two-dimensional vortices is described by the point-vortex model. And we'll often return to some basic results about the point-vortex model in the during this talk. So that's why I thought I'd recap the point-vortex model briefly here. If you describe the positions of the vortices as complex coordinates, their dynamics obey Hamilton's equations given here. And specializing to the case of two vortices, if you have two vortices of identical circulation, they will orbit around each other in a circle about their center of mass. Whereas if you have two vortices of opposite circulation, the so-called vortex-anti-vortex dipole, there'll be a constant translation of the vortices at a finite velocity. And if you have many vortices, the point-vortex model is mathematically equivalent to a Coulomb gas in 2 dimensions. And this is related to the BKT transition that occurs in 2-dimensional superfluids. And the universality of the BKT transition means that the analogs of the point vortex model pop up in several different contexts, and this has been studied since the 1970s. But the point vortex model is dependent on the approximations that you have incompressibility and large intervortex distances. So whereas it does an excellent job of describing the dynamics of vortices in that limit, in superfluids, you often have situations where you can't make those approximations. And when those approximations break down, you get some phenomena such as vortex-vortex annihilations, the emission of sound waves, and so on, which have to be described by microscopic theories, not by a macroscopic theory such as the point vortex model. So for instance, one example that can't be described by the point vortex model because it's two-dimensional is something that happens in 3D where vortices can exhibit excitations of the vortex line. These are called Kelvin waves. And so to give an example of how they exhibit themselves in an experiment, you can see the vortex lines over here with a probe, and you can see that the vortex line is excited helically. So this is a schematic of what that looks like. Oops. And another example of something that can't really be captured by the point vortex model is of the reconnections between two vortices. So to illustrate what this is, you have a vortex of one sign, one circulation of here. You have another vortex of an opposite circulation here. As they come together, you have a topological reconnection where the strands break up and reconnect to form two vortices, but with a different topology. So this is another experimental video of something of a vortex-vortex reconnection in superfluid helium. You have a vortex, you can see the other vortex scattering off it, but the two vortices reconnect and flagellate as energy is emitted after that reconnection. So, well, okay, so these slides were sort of adapted from a more introductory presentation that I gave. So I think we can, I'll go through this really quickly. One example of a superfluid where quantum vortex dynamics exhibits itself is a BEC, where you have macroscopic occupations of bosons in the ground state. So I think I'll skip that. So in the mean field, of course, for sufficiently low temperatures, you can make a Bogoliubov approximation where the many-body field operator for the bosons can be regarded as effectively scalar by taking the vacuum expectation value. And so the many-body Lagrangian can be approximated as a classical Lagrangian with an equation of motion given by the Gross-Petaevsky equation. So this it closely resembles the Schrödinger equation, the one-body Schrödinger equation, but with an additional nonlinearity to account for interactions between the atoms in the condensate. And well, quantitative agreement is evident if you have interactions that are weak. And relevant for the quantum fluid perspective is that you can reinterpret the Gross-Petaevsky equation in terms of a density and a phase and a corresponding superfluid velocity, which gives a continuity equation and an Euler equation for the density and velocity respectively. But the Gross-Petaevsky equation classically only accounts for short-ranged, relatively isotropic interactions. This isn't always the case in atomic gases. Many atomic species have strong dipole moments for which you cannot simply approximate the scattering interactions as being isotropic and short-ranged. You have to explicitly account for the long-ranged nature of the interactions by adding in this dipole-dipole interaction. So if you can think about it in terms of two magnetic dipole moments attached, the atoms being two magnetic dipole moments, if you polarize them along an applied magnetic field, the interaction will be dependent on the angle between the magnetic field and the separation. So if the separations and the magnetic field are parallel, there'll be an attraction. If they are orthogonal, there'll be a repulsion between them. And the interaction strength itself scales with the inverse cube of the distance between two atoms. In an experiment, in principle, you can tune the relative strength of the dipolar interaction to the short-ranged interaction. So this relative strength is given by this parameter here, epsilon dd. And I've also provided some characteristic values of epsilon dd for a few of the more common dipolar species that are studied in experiments. For instance, rubidium-87, which I wouldn't really call a dipolar species, it has quite a negligible value of epsilon dd compared to the first dipolar atom to be Bose-condensed, chromium-52, which has a value of epsilon dd of 0.15. And moving on to more recent dipolar species, such as those from dysprosium or erbium, or the relatively recently condensed species of europium, you can see that they are of the order of 1 compared to rubidium, which is on the order of 10 to the negative 3. So whereas you can discount the contributions of the dipolar-dipole interaction for rubidium and other alkaline species, you cannot do the same for rare earth metals such as erbium and dysprosium. So to model BECs of such dipolar species, you have to explicitly incorporate the dipole-dipole interaction into the Gross-Berdiaevsky equation. So this gives you a modified Gross-Berdiaevsky equation, which I've expressed in dimensionless units. And the dipole-dipole interaction has a Fourier transform given like so. And if you linearize your solutions around a uniform background, you get a stability criterion such that according to this form of the Gross-Berdiaevsky equation, the uniform solution is stable only when the parameter epsilon dd is between negative 0.5 and 1. Of course, in recent years, stability has been found to exist for values of epsilon dd larger than 1, but this requires corrections to the Gross-Berdiaevsky equation that accounts for quantum fluctuations. And so I won't be discussing that here. I'll only be discussing values of epsilon dd less than 1 or greater than or equal to 0. So this arises from finding the Bogolubov spectrum and looking for negative values of omega squared. And likewise, from this, you can obtain the speed of sound, which shows you that in a uniform background, the speed of sound, unlike in a BEC with isotropic interactions, the speed of sound and thus the critical velocity for the formation of vortices is dependent on the direction between the propagation of sound waves and the applied magnetic field. So you can already see that even in the simple case of a uniform dipolar BEC, there are some startling differences between this and a non-dipolar system. So since this talk is about vortices, I should talk about how vortices manifest themselves in dipolar BECs. So after the first dipolar BEC was synthesized in 2005, it took until 2022 for vortices to be observed in a dipolar BEC. So this was done by trapping a dipolar BEC in a harmonic trap and rotating the applied magnetic field to induce a dynamical instability which caused the density to form a spiral pattern followed by the entry of vortices from the edge, like so. This was a theoretical prediction from a few years before the experimental realization via the same method. And there's some other interesting properties that occur in dipolar BECs beyond the formation of vortices. For instance, in the mean field, if you, as I said, if you take the value of epsilon dd greater than 1, or if you tune the short-ranged interaction such as it's attractive, the condensate will collapse and then subsequently expand. In a non-dipolar BEC, this is an isotropic process. But in a dipolar BEC, taking the interactions into the attractive regime results in a collapse and subsequent expansion, which takes on these lovely D-wave patterns, which reflects the inherent symmetry of the dipole-dipole interaction. And if you have a sufficiently strong dipole interaction and large enough densities, as I said, sometimes the role of quantum fluctuations cannot be neglected. If you have sufficiently large densities and sufficiently large dipole interaction strengths, you have to include the quantum fluctuations. And this has been seen to predict the formation of a super solid phase, which was subsequently observed in 2021. So you can see here in this regime, you have a periodic corrugation of the density, accompanied also actually by phase coherence across the corrugations. One aspect of dipolar BECs that I'll briefly return to is the Roton spectrum. So if in confined geometries, a dipolar BEC exhibits a Bogoliubov spectrum that looks like this, you have a phonon spectrum, and you have a phonon mode rather, which subsequently softens into a Roton dip. And if you increase the value of epsilon dd, the Roton dip softens and softens until you get an instability over here. So this is basically the justification for why you get supersolids. But if you think about this from a different perspective, this is quite important in terms of the structure of vortices in a dipolar superfluid. So a Roton is essentially a localized so let me start again. If you have a depletion of superfluid due to strong confinement in one direction, or alternatively, if you have a vortex where there's an absence of atoms, you can get screening of the dipolar interaction due to virtual dipole moments in the region where you don't have atoms. And this results in an interaction between the virtual dipole moments and the real dipole moments, resulting in an accumulation of atoms in one axis, but not in the other. So you get an anisotropic corrugation of the density. And this turns out rather to be quite important for vortex structure. I'll skip this on this side and I'll focus over here. So if we think about the structure of a vortex in a dipolar BEC in a harmonic trap, this theory paper from 2006 focused on a vortex at the center of a harmonic trap with the magnetic field polarized along the x-axis. And what they found is that you have an elongation of the vortex core along the applied magnetic field, which is also accompanied by an elongation of the condensate along the applied magnetic field. So you can see that over here. But interestingly, they also observed that the phase profile of the vortex is anisotropic as well. We were interested in the following. In this theory paper, this effect could have been due to the presence of trapping, or it could have been something inherent to the dipole and dipole interaction. But it turned out that this hadn't been investigated in a completely uniform system. So, well, that's what we did. So we initialized a vortex at the center of this grid, and then we considered dipolar orientations either parallel to the vortex or orthogonal to the vortex, so along the x-axis. And what we find here is the following. If you have no dipole interaction at all, the vortex core is completely isotropic. But then as you increase the dipolar interaction strength, you get an elongation of the vortex core. So this is consistent with the earlier theoretical results, but this is in the absence of a trap. And you can interpret this in terms of the hydrodynamic equations. So in the hydrodynamic equations, you have the interactions appearing in the Euler equation. And then if you have a right-hand side for the Euler equation, which is anisotropic, the velocity profile must also be anisotropic. But the velocity profile turns up in the continuity equation. So if you want a stationary solution for the density and the velocity, which you also need anisotropy in the density. So this results in anisotropic densities and also anisotropic velocities. And in addition, we find that the phase and velocity are not those of the non-dipolar vortex. This is again due to the continuity equations, where if you have anisotropy of the interaction potential, this gives rise to an anisotropy of the density, and thus the velocity. But at the same time, the vortex phase, which normally would have been incompressible, must now be compressible because you've now introduced an anisotropy of the velocity profile. So what does that look like? We have three different figures here we've got epsilon dd here being 0.3, here it's 0.6, and here it's 0.9. So in the first row, we've got the discrepancy between the local value of the density and the angular average of the density. So in all three cases, the magnetic field is parallel to the x-axis, and we've got an accumulation of density on either side along y and a depletion along x. And this depletion and accumulation, the magnitudes thereof, are larger as you increase the strength of the dipole-dipole interaction. This is accompanied by a discrepancy of the phase compared to the classical quantum vortex phase. So in the second column, we've got the discrepancy between the true phase of this dipolar vortex and the classical phase. So you can see that for both of these, you've got lobes of, sorry, you've got lobes of discrepancy where the phase increases more than what would be expected for the non-dipolar vortex phase, and then it increases slower, increases faster, increases slower, and so on. And this discrepancy similarly increases as you increase the dipolar interaction strength. And for comparison, we have the expected value of the dipolar interaction potential due to the vortex density. And you can see that the dipolar interaction potential's expectation value is inversely proportional to the vortex density. So in other words, when the dipolar interaction strength is large, you have a depletion of the vortex density. And if you have a smaller dipolar interaction potential energy, you have more atoms accumulating themselves. So this is somewhat akin to what would happen in a confined system with a dipolar interaction potential, where you have more atoms than normal accumulating themselves near the boundary, near the confining potential. How does this affect the vortex dynamics? So we then proceeded to look at the dynamics of vortex pairs, either of same sign or an opposite sign. So first I'll talk about the dynamics of same sign vortices. In all of these cases, they're of positive circulation. In the point vortex model, as I said at the start of the talk, you expect circular trajectories of the vortices about their centers of mass. This is not the case when you introduce a dipolar interaction with the magnetic field orthogonal to the vorticity. It turns out that the dynamics are unaffected when the magnetic field is parallel to the vortices, but in the orthogonal case, you get trajectories that deviate quite significantly away from the circular paradigm. So these are arranged in terms of their initial separation. The initial separation here is roughly 3.125. Here it's 6.25, and here it's 12.5. So for small initial separations, the vortices are roughly roughly circular but slightly elliptical along the y-axis for a small dipolar interaction strength. But as you increase the dipolar interaction strength, it becomes more oval, and then here it becomes dumbbell-shaped, reminiscent of the Cassini oval. The same thing happens for larger separations, but there's less of a deviation. And then here, for large separations between the vortices, you can barely see the discrepancy between, from circular orbits. So we believe that this is due to the fact that as the vortices orbit each other, the dipolar interaction potential experienced by one vortex with regards to the other is not going to be isotropic, because as the vortices orbit each other, the local dipolar interaction energy will always look like this in the vicinity of the vortices. But given that this isn't isotropic, the value of the dipolar interaction energy at the position of the other vortex is going to be time dependent as it goes around in its locus. And so the positions of the vortices readjust themselves in order to minimize the dipolar interaction energy, but at the same time mutually minimizing the energy arising from the kinetic energy of the vortices themselves. So there's an interplay of the vortex-vortex hydrodynamic energy from the phase and the flow fields of the vortices, and also the dipolar interaction energy arising from the presence of the other vortex. So this isn't a consideration that arises in non-dipolar vortices, where the corrections to the velocities and the trajectories of vortices due to the compressibility of the fluid is still going to be isotropic. And so although you might get different velocities of vortices, the orbits are still going to be circular for large enough distances. But here we see that even at distances as large as 12.5 distance units, you still get a small but noticeable deviation away from circular orbits. Now, if you have opposite signed vortex-antivortex pairs, for the same sign pairs, we've seen deviations away from circular orbits. For opposite sign pairs, it turns out that you still do get the trajectories of the vortex-antivortex pair being a straight line along the binormal of the vortex separation, which is the classical point-vortex result. But whereas the point-vortex model, or the three-dimensional generalization of the point-vortex model, the Biot-Savart model, predicts a universal velocity for the vortex-antivortex pair, dependent only, provided that you've appropriately d-dimensionalized your equations, dependent only on the separation of the vortices. When you have a dipolar interaction, we find that the velocities of the vortex-antivortex pair are strongly dependent on the orientation of the magnetic dipole moments and also the dipolar interaction strength. So firstly, we find that when the magnetic dipole moments are polarized parallel or anti-parallel to the vortices, there is no change in the velocity. So in these figures where we've got three initial separations and we're tracking the velocities of the pairs, if you have dipole moments which are parallel to the vortices, the velocity is always going to be the non-dipolar value. But if we focus on the other two cases where the dipole moments are polarized orthogonal to the vortex separation, which is the blue axis, or parallel to the vortex separation, the red curves, we find that in all three cases, except for what happens for small separations for very low values of epsilon dd, we find that the vortex-antivortex velocities decrease as a function of epsilon dd, attain a global minimum for some intermediate value of epsilon dd, and then increase. Whereas if the, and that's what happens for, and the dipole moments are orthogonal to the vortex-antivortex separation. So here in these simulations, we had the vortices separated along the y-axis. So when the dipole moments are parallel to the x-axis, the velocity generally decreases for larger and larger epsilon dd's. Whereas for parallel separations and parallel dipole polarizations, the velocities monotonically increase. So this is quite a stark discrepancy compared to the non-dipolar paradigm. We believe this is, again, due to the fact that you have to balance the dipolar interaction potential and also the kinetic energy from the flow between the two vortices. And these ideas can be extended to 3 dimensions. So some work that we've been doing at the moment is considering the effects of the dipolar interaction upon the evolutions of Kelvin waves, which are excited upon 2 vortices which are anti-parallel. So in classical fluid mechanics, you have a similar situation that occurs on the wingtips of aeroplanes. So you have vortices on the wingtips of aeroplanes, and these are perturbed by waves from the engines and so on. And this results in Kelvin waves being formed on the wingtip of vortices, and certain modes become unstable. And so these become larger and larger and larger until you get reconnections, which are forming vortex loops, and which then subsequently cascade into smaller and smaller loops. So if you look up at the sky, you'll see that the contrails of aeroplanes have often become fragmented, and this is the this is a physical explanation for why those contrails become fragmented, due to the vortices forming loops which subsequently cascade into smaller and smaller loops. So this has been studied in quantum fluids as well, in BECs. And we wanted to look at how the dipolar interaction affects this, because if there's a deviation away from the non-dipolar paradigm, this would have ramifications for the way turbulence manifests itself in dipolar BECs and so on. So what we did is we initialized a vortex dipole with the separation along the y-axis. We populated the lowest 20 Kelvin modes supported by the box length on each vortex, and we propagated the Gross-Bertevsky equation to observe what happens to the vortices. So this is a non-dipolar simulation. So the vortices move along the x-axis, but then the Kelvin waves have grown larger in amplitude until a reconnection forms over there. So you have the vortices break up into one big loop, at least topologically speaking, because we have periodic boundary conditions. And you get a second loop forming and a third loop forming. And here, and also a rarefaction pulse over here, which travels much faster than the other vortex loops. So we can look at this rather than 3D. We can look at two-dimensional cross sections to see what's going on. Let me play that. So initially the amplitudes of the Kelvin waves are rather small, but some of the modes have become dynamically unstable and are thus growing exponentially in amplitude. You can see that over there. And this is the direction of propagation along the x-axis. So you have curvature of the vortex parallel to the direction of propagation, which then induces a back reaction upon the vortices, causing further curvature. And so the fact that the vortices are coming closer together results in this segment of each vortex moving further along. That back reacts, and so on and so on. So that's the origin of this dynamical instability. You have a reconnection there, two loops, and more loops subsequently form. This, of course, is the non-dipolar case. How does this how does the dipolar interaction affect the Crow instability? Do you have the same reconnection times? Do you have the same modes being excited in this dynamical instability? Or are these intrinsically dipole-dipole dependent? So what we've done is we took several different initial Kelvin wave profiles, and we have investigated a range of different dipolar interaction strengths and polarizations of the dipoles themselves, either parallel to the net vorticity, parallel to the vortex separation, or parallel to the vortex-vortex propagation direction. So, and what we find is that if you have the dipoles polarized parallel to the propagation direction, the time taken for the vortices to reconnect increases monotonically as a function of the dipolar interaction strength. On the other hand, if you have the dipoles polarized along the separation axis, you have a monotonic decrease of the reconnection time. So reconnections, the first reconnection happens earlier as the dipolar interaction strength is increased. And then if the polarization direction is parallel to the vortices themselves, we don't observe a monotonic behavior in the reconnection time. So this is for one initial Kelvin wave profile, averaged over several of them. There is no clear trend. So we attribute this basically to the opposite sign pair dynamics over here for straight lines in the same system. So what we saw here is the velocities of the vortex-anti-vortex dipoles were faster if the dipoles were parallel to the separation, and slower if they were polarized parallel to the propagation direction. And if we look at this, we see that the times are longer wherever the velocities are smaller. And for larger vortex-anti-vortex velocities, the reconnections happen faster. So it would seem to us that a certain distance needs to be traveled by the vortex-anti-vortex pair before reconnections occur. That would be the universal quantity. So there are quite a few extensions that we can look at. For instance, you can track the mode population of the Kelvin waves. This is still early work in this case, so I've only presented the non-dipolar results here. For small times, you have a large spread of population across multiple Kelvin wave modes, but as time moves on, certain modes are excited preferentially to others, and one of these is going to ultimately the one that results in the reconnection. Tracking the amplitude of that mode, you see after some initial readjustment, you see exponential behavior, an exponential dependence of the amplitude of that mode with respect to time. So on a log-log plot, it's largely straight. And similarly, the distance between the two vortices as the vortices approach each other before the first reconnection is exponentially dependent on the time taken to the reconnection. The non-dipolar prediction for the exponential scaling is 0.5. Something we'd like to look at is if the intervortex separation scalings are dipole-dependent. So to wrap up, the dipole-dipole interactions alter the vortex ground state densities, the phase profiles, the trajectories of two vortices, whether they be same signed or opposite signed, as well as the reconnection properties of curved vortex lines. So that raises several questions. In 3 dimensions, the Beer-Savart model is an effective description for vortex-vortex dynamics. Do you have to modify the Beer-Savart model when you have dipolar interactions? Similarly, what would modifications to the point-vortex model look like? Similarly, you can see an exponential scaling in the intervortex separation. Does the distance scale as 0.5, or is there a dipole-dependent modification to that scaling? How does the curvature and the torsion of vortex lines behave during a dipolar reconnection? You can also talk about the line length of vortices. Does the decay of the line length of vortices after the reconnection as they form loops scale in the same way as it does in the non-dipolar system? And you can also extend this to look at time-dependent dipolar polarizations rather than having a static dipole polarization. So can you induce novel vortex dynamics or even turbulence scenarios by having a time-dependent dipole polarization? So these are future directions that we're very much interested in. So we're currently writing up the vortex reconnection work, but there's a preprint out there on the static and dynamic properties of straight lines, straight vortex lines in 3D homogeneous dipole BCs, which I strongly encourage you to look at. And lastly, I'd like to thank my PIs, Andrew and Nick. Thank you.
Yeah, thanks, Rata. So are there any questions? Or just unmute yourself and go ahead with the question. Yeah, Patrick.
Hi, thank you for a very nice presentation. I'm wondering, did you guys try to simulate the decay of multiply quantized instabilities?
We haven't, no. It definitely would be an interesting thing to look at since in modified BECs, shall we say, like if you have more than one species and so on, you have modifications to the stability. No, this is definitely something that we probably should look at in future investigations. No.
Right. I'm looking forward to that. Thank you.
Thank you.
Thanks. Any other questions? Yes, I'll ask a question. So in one of the earlier slides, you showed a ground state with a square vortex lattice.
Yeah.
So what can you tell more about it?
Yeah. Yes, of course. In dipolar BECs, the dipolar interaction means that you don't just have the possibility of triangular vortex lattices. I believe there are people in the audience who can definitely tell us more about this. But essentially what happens is let's consider this state over here. You have basically the dipoles polarized along the x-axis over here. And the vortices, of course, they basically form a channels, so to speak, for the density to follow along. So if you have the density profile elongated along this direction, there's an energy cost compared to having the density profile along here. So you have an energetic preference for the densities in general to be elongated along x, not y. But the vortices themselves are likely to be found in positions in regions of low density, meaning that if you had densities elongated along y, where you have dipoles polarized along x, that there would be a strong energy cost associated with that. So as a result, for intermediate interaction, intermediate dipolar energies or angles in this case, firstly, you have stripe phases that occur where the vortices don't form triangular lattices like that, but you have lines of vortices and stripes between them. And then as you increase the dipolar interaction even further, or if you increase the angle between the vortices and the dipoles, the striping becomes even more evident, and the striping is what induces the square lattice. I hope that helps.
Yeah, well, thanks. Yeah, certainly when you add more interactions, things get more complicated. So, sure.
So I'm just curious with these dipolar BECs. I mean, do the dipolar interactions in any way inhibit or enhance annihilations between vortex anti-vortex pairs? I'm thinking of 2D systems now.
So there was a paper about 10 years ago that looked at vortex anti-vortex dynamics in quasi 2D systems with strong trapping along the Z direction, where the vortices are parallel to Z. And what they found is due to basically rotons, depending on the direction of the dipole moments, you could actually suppress vortex anti-vortex annihilation. So of course, conventionally, if you have two vortices and you have significant core overlap, they will annihilate, right? But for strongly dipolar BECs in this quasi two-dimensional geometry, you had suppression of annihilation, but we don't see that in 3 dimensions. So everything I studied here talked about was 3-dimensional. You don't see that in this system because you don't have rotons. We do have an accumulation here and here, but you don't have the periodic corrugations of the roton. But yes, you do see that in 2 dimensions. That's correct.
Okay, thank you.
More questions? Well, if there are no questions, well, thanks a lot, Srivasa, again, for
Thank
giving this seminar. And our next webinar is in 2 weeks' time. So it's going to be Marco Lamantia from Prague. So I'm hoping to see you then in 2 weeks. And thanks a lot for attending the webinar.